Hello and welcome to Prototype and See, a brand new podcast for designers, engineers and innovators all about the product development journey. My name's James Murphy, co-founder of HLH, one of the world's leading manufacturers of prototypes and low-volume production parts. I've been in this industry for nearly 20 years, but I feel there's still a great deal about our customers that I don't yet understand. So, in Prototype and See, I'm going to be sitting down with some of the world's most innovative companies, talking to designers and engineers, all about the successes and failures, the ups and downs of bringing new products to market. Today, we're very honoured to have with us both Daniel from HLH and Rich Walker from Shadow Robot. Hello, Rich. Thank you for coming on.
Thank you for having me.
Okay, could you just briefly tell us who you are and who Shadow Robot are?
Sure. I'm one of the directors at Shadow. I've been involved with the company since its founding. We have a kind of complicated history, so there's no one founder of the company, as it were, as a group of us who were there at the beginning. And I've been primarily working on came in as a technical person, came in wanting to do software engineering, develop AI software for robots, ended up building the robots, ended up designing the robots, ended up fundraising, ended up developing technologies, working with people to build partnerships, build R&D programs, work out ways we could make new and creative things, and basically do the kind of business development side of how do you build really innovative new creations in the space of robotics.
Okay, and you talk about robotics, but I think you manufacture a specific type of robot. Could you tell us a little bit about that?
Yeah, we started out very much building things that were interesting for us. We built a biped back in the 1980s, which we carved from maple.
Right.
Because honestly, maple's a really nice material to work with if you're prototyping and you can get hold of it. It's kind of hard to get, but it's a great one to work with.
Okay.
We found load and a skip.
Right. Yeah.
We gradually moved on from that, and we moved into building hands for robots.
Right.
And there were two reasons for that. One was Honda seemed to be throwing a lot of money at building bipeds, and we were kind of like, "Oh, £800 gorilla in the room. Let's move somewhere else."
Okay. Yeah,
and the other was we thought, well, actually, hands are really interesting because everything in our world is built around the hand. It's built around the ways we interact with it, the things we do with it. So if a robot is going to do all the things that we can do in the world, then it's going to want some way of interacting with all the same objects. And we thought, let's build hands.
Okay.
Those seem like really good things to build.
I believe you're one of the UK's longest running robotics companies. Is that the case?
It's a curious distinction when you're still you think of yourself as a startup and yet you've been doing this for over a quarter of a century. It's a kind of unusual place to live in, but I guess it's somewhere that we really like. We maintain that kind of creative enthusiasm, energy and innovation, but we have a kind of longevity and depth of the company. I mean, we have people working with us who've been with us since we moved from being a bunch of people having fun to a formal legal entity, and that was in 1997.
Okay. And how difficult is it to keep a company going in an industry such as robotics? There must have been, over the years, you must have seen hundreds of companies come and go, and yet you're still here. So how have you done that?
I think we've been lucky in several ways. One of the people who was involved right from the very beginning, Richard Greenhill, he was lucky enough to have premises in London that we could use. And free office spaces, not free workshop spaces, not to be sniffed at. That's a massive, massive win. And we were always doing it because we wanted to do it. So there wasn't really a sense of people going like, well, I'm not earning enough doing this.
Right.
There was a sense of people going like, how can I get to do this thing? Oh, I need some money to do that, to make that happen. We were lucky enough to have some really good early clients. We found a few people who were there's a great book on the customer-funded business, which talks about the 5 ways you can start your business without needing lots and lots of capital. And essentially, it's get the customer to back you at some level. And we had a couple of those. So they were able to put money in early on and say, well, we can pay you a down payment if you build us this thing, and we'll pay you when we get it.
Okay.
And that helped a lot.
Okay.
And also, they were kind of willing to back building quite complicated, innovative things that they knew might be really, really hard to do. And they were kind of expecting, like, this is the first delivery. Can you accept payment? And there'll be a second delivery in about 4 weeks. And they're like, yeah, sure, we understand that. Yeah. Because their view, and it's a great view, was if it's at the state of the art, it's going to be delicate, it's going to be fragile, it's going to be like, yeah, sorry, it didn't work this week, we'll fix it, it'll work next week. Because if that's not happening, it's not actually right as the limit of what's possible.
You're not pushing the boundaries
if
of what's
it's
possible.
rock solid, reliable, works every time out the box, then it's standard technology. And they were coming to us for innovation, so they wanted that kind of really pushing the edge, kind of almost risky proposal on the table.
Okay. And in art, people say like sketching a hand is like one of the most difficult parts of the human body to actually sketch. Like, would you say that's the same for like robotics? Because it's a very complex.
When you look under the surface, it's worse. There's muscles all over. Some of them are down here, some of them are up here. There are tendons. There's this fantastic sealing material that goes all around the outside that's elastic and also does sensing for it. There's there are joints that lubricate themselves. I mean, there are things in there that you're just, as an engineer, you're like, this is phenomenal. How did that happen? How did it? And then you start trying to do it, and you're like, yeah, well, we're going to put all the motors over here, and they're going to, our forearm ends up being a huge Popeye type thing because we just can't pack the motors as densely as you can get the muscles in the hand, and we don't have the same kind of technologies to be able to do skin. Every so often, someone says, "I've made a new skin for robots," and we'll go and have a look at it, and we go, you've got about 30% of the functionality. It's a different 30% to all the other ones. If you can just combine them all, that would be really good. And they'll come back and go, we can't do that yet. Can't do that yet.
Right. Okay. So for things like the skin, for example, you're working with external partners, or that's something that you're developing yourselves?
We've done both sides of that game. It's one of those things when you're trying to do something that's right at the edge. It's sometimes you find someone who can do a bit. And sometimes they can't, and you can't do it, and so you have to learn to do it yourself. And but you're always making that buy, build, subcontract kind of mental trade-off, and saying to yourself, if I find somebody who can do this better than I can, then I'll get them to do that, because then I can focus on doing this bit.
On the bits
so, for example, for many years we worked with a California company called SynTouch, and they make the best fingertips for robots in the world, by far and away the best fingertips. Everyone's like, yep, the SynTouch BioTac, absolutely the best sensor. So we basically haven't bothered, because
you're trying to develop your own.
But we track the technology, we build some prototypes, we do some experiments around it, because we might find a better sensor, we might find a better approach, or we might have a customer who says, well, I don't want that, I want something a bit different. The SynTouch sensor covers the fingertip, but it does nothing for the palm. So there you need some different technology, and so we end up getting involved with people. Sometimes they're doing a PhD, sometimes they're running a research department, sometimes they're pulling together a research project, a big project, and looking at things. And we get involved and go, okay, let's understand this technology so that we can work out when we can do, great customer over here, we can get this new stuff. Do you want this new stuff? And be the people who kind of bring that over sort of from TRL3 to TRL5, maybe 6. But we tend not to go much further than TRL6.
Right. Okay. And each individual robot that you build is specific to the application, so you build them for different use cases. Can you talk a little bit about that?
So most of our customers are doing a similar thing, which is they're doing research in robotics technology. They're trying to understand the art of the possible. They're trying to implement that. Maybe they've got a fantastic machine learning department and they're trying to use that in the real world. Maybe they're doing robotics algorithms. Maybe they're looking at ways to use robotics technology in some problem space that they have. So we supply them with the hardware to do that. Most of the hands we build now are pretty similar to each other because we've been doing it for a while. So there's a kind of consistent platform. But occasionally someone will come along and want something different, want a special, want the whole thing to be a foot longer for some reason. Customer says they want this, you price it. If they agree on the price, then you build it. But the first generation and the second generation and the third generation we built were all absolutely everything in there was totally unique. I mean, the first hand we built was hand carved out of wood. The second one was mostly cut out of thin perspex sheets that we then filed the edges of in a curious way with Dremels and kind of fastened them together with bits of aluminium that we pretty much hand filed into sizes like 1998, 1999.
And today, is it mainly 3D printing you're using, or what kinds of technology?
We're quite opportunistic about the technology. We've been through that phase where you own milling machines and you own we've been through that phase of owning milling machines and kit of that type, and these days we don't do that because as you know, owning machinery is a specialism, right?
Yeah.
You need to be good at
Yeah.
it. You need to have someone who's absolutely passionate about getting the right ball-nose drill bits from the right company.
And it takes
keeping
you
the
away from what you can.
Yeah, so
better
if someone
spend
else
your
can
time
do
on.
it better than us, cheaper than us, faster than us, then of course we just push the work to them. But then there are other things where you're like, okay, we actually need to have, like, if we hit print now, in 3 hours' time, we can be putting that piece into a prototype, into a test. So we do that. And then equally, we have bits where we're like, well, if we go to the bandsaw now, in 10 minutes' time, we can have a piece that we can be using and testing. So we've been doing some feasibility work for a customer at the moment, where literally there are things there that are wood held together with string and sealing wax, because that was the fastest way to make something.
Fastest way to do something. Yeah. And often that's all you need. Yeah.
It works. Okay, now we can build it right. Or it doesn't work. Okay, change the design.
Yeah. And in terms of like building the robots themselves, like has 3D printing and technologies like that, have they kind of freed you up from a design perspective, enabled you to do things that you weren't able to do in wood?
We've kind of gone around that loop. When 3D printing first became common, you'd have these people 3D printing fantastic, like, Klein bottles and objects that you couldn't assemble, but you could print them and things. And we all looked at it, wow, that's absolutely amazing. And then the service guys said, well, yeah, but when it breaks, how do we fix it? And we all went, yeah, you're okay. If you can't assemble it, you can't disassemble it, and that means you can't repair it. And a lot of what we do with our customers is maintain things that they've broken because they're at the state of the art, right? That's going to happen. So, yeah, you can swap out a part for a replacement, but if you've built some electronics cunningly around that part and you've got some tendons going through it and then just pulling a bit out and replacing it might not be feasible. You might actually need to be able to dismantle it and put it back together.
Yeah. Okay. And what is the most kind of complex part for you guys to design and manufacture? I'm
going to say that the wrist is insanely difficult,
right?
Because we have 20 pairs of tendons running through the wrist, 40 tendons in total going up into the hand, and ideally, they'd all go through the exact center of both of the joints.
Yeah.
Obviously, none of them can go through the exact center if all of them are going through the exact center. So there's a whole routing and packing problem, getting all these tendons up from the motor base up there, through there, and around there. And you look at it, and it's a nice shiny piece of aluminium. You wouldn't think anything of it. And it's like, but actually, that's had a huge amount of effort put into, and that tendon's going to go there, so that'd be like that. And it's one of those things where it's hugely complex and it just doesn't show at all.
Yeah. And your robot is designed to like as closely mimic the human hand as is like conceivably possible.
Exactly. We literally had two people sitting across the desk from each other, and one of them would hold their hand up and the other one would take measurements off it. So the fingers are the same size as one of their fingers and the thumb is the same size as the other one.
Right.
And there was about a year where we had a running argument over whether or not we could afford an extra millimetre of space on the palm, because that would have made the electronics easier to do. And eventually we didn't afford that extra millimetre of space on the palm. And so we have pretty much the same ergonomics from there up as the human hand.
Okay, and the reason you've done that is essentially just because the human hand is the best way of doing it.
Reality has been optimised by us for the human hand. If we had 6 fingers and 2 thumbs, then our reality would look slightly different. If our hands were a lot bigger, our reality would look slightly different. As it is, pretty much everything here is optimised around the human form and shape. So we figured build for that, copy that, because that was it gives you the existence proof, right? You know a human hand can do it, so a robot with that hand should mechanically be able to do it. Now, can you do it in software? Can you do it in AI? Can you get the vision system to work? Can you do all the other parts of the robotics game? That's a separate problem, but at least you know that mechanically the hand is compatible with the human hand.
Okay. And of those two problems, which is the trickier, the software side or the hardware side?
I would say that the mechanical design and the engineering around getting a robot hand to work in the first place is one entire stack. And then understanding the world and seeing the world and understanding how to interact with objects and what humans do when we do that is a completely separate other stack. And they're both huge problems. I mean, we've spent over 20 years working on this side of it, and there are entire research departments who've spent their entire research history working on the other side of it, and still, robots are not really wandering around the world picking things up and giving them to you in a convenient way.
No, not yet.
Not yet.
When will we see that?
Well, we're seeing a lot more robots that do useful things in the world now. The whole term service robots, which kind of got made up about 20 years ago as a way of saying it's not a robot on a production line. What is it? Oh, it's helping somebody. It's doing service. It's a service robot. And so there are now regular kind of competitions around this. There's the European Robotics League up in Milton Keynes in September, where they'll have service robots competing, doing useful household tasks, useful social tasks. But even when you look at the kind of state-of-the-art humanoids coming out of the US companies, they still don't have lots of dexterity, they still don't have mobility, they still don't have understanding of the world. That's going to be a game changer when it happens, but we're not sure who will get there first or how.
Or when.
Or when.
Yeah. So I think for Shadow Robot, something that's important for you guys is robotics for good. I think you that's how you term it. Am I correct?
Yeah.
So
we always felt that it's very easy to get caught up in the excitement of what you're doing and not look at the implications of who you're doing it for and what it means and what would work if it happens. So we always felt that it was kind of it helped us sleep at night if we were able to say to ourselves, yeah, we've thought about this and we've looked at it, and with a clear conscience, we're happy with it. We can do it. So we do look at kind of potential projects, potential customers, and say, would we be happy doing that? Would we actually say to ourselves, yeah, that's interesting, it's fun, and it's done some good? Or would we say, yeah, that was interesting, yeah, that was fun, but let's not put it front and center of the website. And it's perfectly feasible. Building a good company is a discipline. It's a process. It's possible to build a good company that does things that I might say were bad things. Any company that makes weapons systems, in my mind, is kind of doing bad things, but it could be a fantastic company to work for with a fantastic culture. But we don't want to be a good company who are doing things that we don't think are kind of ethically proper. And it kind of keeps us on our toes to do that, to say that, and it helps a lot as well when you're talking to people who might work with you to be able to say, we have this ethical, we have these values, we have a purpose, and we have an ethical policy, and we turn work down if it doesn't fit with it.
Okay. So in terms of that kind of like ethical policy, like where do you stand on like the future of AI and where that's going to take us? And
I'm kind of disappointed that the big breakout thing for AI is doing fun stuff like writing fiction and drawing stuff and arguing with people. It's kind of like, couldn't you have done a boring job first? That would have kind of been more interesting. And I've taken a look at all these kind of tools and said, oh, yeah, okay, this stuff is generating interesting things and it's generating plausible stuff. But honestly, if I want plausible bullshit, I'll go down my local pub. I can get plausible bullshit all day there in a much more congenial environment and have a drink as well. So I think we will see the technology doing stuff. We'll see applications of it, and we'll see what any large organization will do with this stuff, which is to go, how can we strip out cost? How can we change our work so that we do less of the things that we can hand over to these machines? And some things they will do well. Things like auto-suggestions when you're typing in a Google Doc, and it suggests the next 4 words, and you just hit tab and it's done. And it got them right, so you just hit tab. And those things make life easier, they make life quicker. But then getting it to write the whole text for you, that's kind of a bit, it feels like a cop-out. And it feels like as well that what you're going to get is a whole bunch of bland, undifferentiated kind of spam, very basically, spam.
Okay, but like your product, your robot, like, do you see the potential for that maybe replacing people? And
we talk a lot to people who have problems with skills, and the skills problems they have usually come in the form of, I can have the skill in this place, but not in that, or it's hard to get to that place. Maybe it's because it's a long way away. Maybe it's because that location is just challenging to be in. Maybe it's an environmentally difficult place. Maybe there are constraints on the people who can do it. So they look at that and they say, well, if we put a robot over here and a human over here, we can transport the skills. And we're not reducing the number of people. We're not changing the number of people. We're just moving the skills from A to B. And that we think is very interesting. And obviously over time you start to build up a kind of library of stuff that might be easy to get the machine to do automatically, but you're not cutting the human out. You're just saying, well, the machine can do some of this and then the human can do other parts of it.
Augmentation of...
Exactly. So as an example, we talked to some people who clean things. They clean machinery all day because they have very, very precise process tasks going on, and between process steps, everything is cleaned. You cannot have any powder from the first step in the machine when it's used for the second step.
Yeah.
That's really tedious. It's difficult to get it right.
Yeah.
It's really difficult to get it right every time.
Yeah.
So you have someone does it and someone else verifies it, and then you've got two people doing it, and it doesn't add value. It's just a necessary thing. It's clean the thing before you start work. So can a robot do that automatically? Well, probably. Can we do that by just having the robot copy what a good human operator does to do that? That sounds like something we should be able to do. Yeah.
Okay.
So has there been any sort of object that has been particularly challenging to get the shadow robot to grip or hold?
The first one that someone came up with that turned out to be really, really difficult was I don't know if you remember when the Wii console came out and they had this nunchuck handset with buttons on it. Those were incredibly hard. And the reason they were incredibly hard is they had been hyper-optimized for what the human hand can do. So you're holding something and it's optimized ergonomically to stay in your hand, because the last thing you want is something that you're flicking around like that flying out of your hand. And then it's got buttons on it, and those buttons are in places that your fingers and thumb are naturally resting. And so it was actually taking advantage of some of the elasticity in the hand where it can kind of bend around, and we couldn't do that. That was actually beyond what we'd done, and we sort of went, yeah, okay, that's a really impressive object because it's so well optimized for the human hand that actually we found it really, really difficult to do.
Okay.
How did you deal with that?
We went back to our customer and said, why do you want to handle the Wii nunchuck? Right. And they said, well, we were looking at things and we realized we couldn't do this. And we were like, well, we could probably make these changes and make these developments and so on, but it would take this long. And they were like, we can use some other objects.
Okay.
We don't want people building robots to play Wii video games. That would just be a bit circular.
No. They were just looking for something to challenge you guys.
Exactly.
And how long would you say it took for Shadow Robots to complete the first working prototype, the wood one?
So I think the wooden hand was built over about 5 or 6 months. It wasn't a full-time kind of occupation. It was just to kind of like try these things and do these things. Back then we were using pneumatic technology to drive it, with things we called air muscles.
Yeah.
So they were a nice simple idea. They've been independently invented by 20 or 30 people over several hundred years. And essentially they consist of a rubber tube in a mesh. As the rubber tube expands, it makes the mesh contract. Nice and simple. But those give you a nice kind of elastic thing, which mean that basically you can, if you have a joint that you can move, you can just tie 2 pieces of string to it, put the muscles at the far end and get it to move back and forwards. So that made it quite easy to make prototypes, quite easy to make simple mechanisms. The hard part was then when we went back and said, okay, we can move that joint, but where is it? How do we measure that? And then we had to work on how do we put sensors in? How do we actuate that? But somewhere we've got a video of that first robot hand picking up a pint of beer in a straight glass, because we figured, like, what's uniquely a British thing to pick up and handle? Pint of beer, straight glass. And everyone who's seen that's just kind of like, is that real beer in there? And we're like, well, yeah, obviously, we're in the workshops, of course it's
Okay.
So with the Shadow Robot hand, you're able to feel objects in real time. But what materials were used to develop the touch sensors integrated into the hand?
So we've worked over the years with a number of different touch sensing technologies. We did some research years back with a thing called a technology with a magnificent name of quantum tunneling composites.
Right,
just
so
incredible
stuff. It is a good name.
It's
a
great name for something.
Yeah.
And that was a kind of worked for some things, didn't work for others. The fingertips that we work with now, these guys in California make them, and they're actually a really interesting mix, because what they have is a kind of a rubber dome with electrodes on the inside of the dome, and it's filled with mineral oil. And as you press the dome, the electrodes change in separation, and you can measure the impedance between them. So that gives you where it's being touched.
Okay.
But they also measure the pressure in the oil.
Right.
And that gives you 2 things. It gives you kind of an overall how hard is this thing being pressed, but also if you move across a surface, you can see the vibrations in the pressure. And that lets you understand the kind of surface roughness that you're touching.
Wow.
And they measure temperature as well. And it turns out that if your sensor is nice and warm and you touch something metallic, it cools down quickly, and you can see that, or you can measure that and go, aha, I can tell the surface properties of the thing I'm touching from the way the sensor responds to it. So that's a really cool sensor.
Yeah, okay. And obviously you work with different companies all over the world to develop your product, and the people that you develop them for, they're also global, or is it mainly the UK?
Absolutely. Our first customers were in Germany and the US.
Right.
And we were kind of like, we were slightly confused the first time we had to pay UK tax because we'd done business in the UK, because that had never happened before. We'd always been selling stuff overseas.
Yeah.
We talked to people who do export support, and they'd say, so how much of your business export? And we'd like, 96%? And they were like, okay, can we help you sell in the UK instead? Well, maybe. That's it. But it's
is that still the case? Or?
We've got a couple of customers in the UK now who are fairly substantial, but still most of our business is overseas. Robotics is a global. It's science, right? Science is global. People do science all over the world.
Well, obviously,
so
there are some countries that are kind of leading the way in terms of robotics. Like America must be
America, China, Japan, Germany, Italy. Those are all places that we spend a lot of time flying to. Yeah.
Okay.
Yeah.
But the scene in the UK is healthy. Or?
The UK has a lot of stuff going on. So there was a kind of strategic view 7, 8, 9 years ago to invest in UK robotics technology in universities, and that got done quite well, and it built up a bunch of expertise, a bunch of universities that are pretty good at developing PhD students, which is what universities are really, really good at.
Yeah.
So you got a pipeline of people with PhDs in robotics coming out of that, and you get departments that then have a good pool of people to choose from to do interesting things. So from that point of view, the UK has had a pretty good technology
all
base.
All academic though, or
a lot of them are doing a good line in teaching their students how to transition, how to move from academia into SME, into the startup world. I think particularly of Imperial and Bristol and Edinburgh, Heriot-Watt, all three of whom have an excellent track record of helping their students go out into the real world and set up businesses, and then find funding for those businesses and grow them and get them to do new and exciting things from there.
Okay, and you work a lot with those institutions?
We have the advantage of, like, we have this hugely long record reference list. So we've been around for years, so everybody knows us. So when they're looking for people, they're like, oh yeah, we want some people to come and help us understand what we should be doing and how we should do it, and then they tend to ping us first because they know we're interested. We care about that.
Yeah.
We've been doing this for a long time. We do it because we're passionate about it, and we kind of really understand that robotics is one of those areas that inspires people. If you're trying to get someone to study hard equations in school, showing them they can build a robot with it, it's kind of a really good way to do that. That's like, no one wants to learn control theory until they try and get a robot arm to stop precisely. Suddenly they're all about the control theory and learning about moments and jerks.
Okay, so do you get involved in education in that way as well? Like, do you going into schools and
we've done a bit of it. That tends to be more responsive. So somebody will get pinged by one of their school. Our engineers now have their own kids in schools, so the schools are like, come and talk about what you do, and we have parent come in and talk evenings, and so they're like, can I borrow a robot hand? I'm going to my local school, and it's like, yeah, sure, come in. And so we do that, and that's kind of very organic. That's people who want to do it because they know what they're doing. At the kind of more university level, we tend to be doing guest lecture stuff where it's like they phone you up and they're like, hey, can you come and give a talk to a bunch of people about what it is your company does and how they do it? And I get up when I do those talks, and I reassure them by saying there'll be no equations in this talk. If you want an equation, ask Professor so-and-so, he can give you the equations. I'm here to tell you what you do when you've got the equations.
Okay, all right. So for you, what's like the most difficult thing about building robotics?
There's an old joke that supercomputing is 90% plumbing and 10% being able to pronounce gallium arsenide.
Right.
And robotics is like 90% packing, just getting all the stuff in a small
inside,
space, getting it all in there. Sometimes you then run into heat problems as well, but firstly it's how do you get all the things you need in the limited space that you have? And every so often something changes and it suddenly becomes a lot easier to do that.
Right.
So the first robot we built, the original biped, it had one analog to digital converter on it,
right?
Because like that was what we could get and we could afford at the time. So every sensor had a 6-foot cable running to the A to D converter in the head. Crazy design. Right. Now we scatter microcontrollers everywhere that have high resolution ADCs on some of their pins anyway, and a network connectivity kind of designed into the microcontroller, so you can just treat these things as just an embedded distributed system. So that makes some things easier, but then it means you've got to work out, okay, what if I want to change the firmware in that joint there? How am I going to do that? So you still have these kind of systems engineering problems. And someone's like, can you plug a cable in? It's like, I can't plug a cable in there. I don't have any spare pins.
Okay.
So, what are some of the difficulties in creating a hand that can successfully grasp and manipulate a range of objects from delicate to heavy?
It's interesting you say delicate to heavy. So one of the limits we set ourselves was not too heavy. And in fact, our hand, we tend to say to people, like, you can probably grab 4 or 5 kilos like that, but you don't want to go much more than that. And the reason you don't want to go much more than that is the stronger you make the robot, firstly, the more damage it can do if something isn't working. But secondly, the bigger everything gets. And when what we're facing is a packing problem, saying we'll only go up to that strong means that we can avoid some of those challenges. So our tendons can be a bit thinner, and our wiring can be a little bit more flexible because we don't have to pack it through a joint that's got as much load on it. So yeah, that packing problem and the trade-off was kind of really, really hard there.
And how can it sort of determine between like a heavy object and a light object? So I assume different amount of power would be used to obviously pick up a heavier object, so sort of thing.
Do you have to tell it before it does the work? Or
we've actually done this in a couple of ways, but the almost comedy answer is we let the robot arm do that bit. The robot arm is responsible for the kind of the power lifting part of the job. These days most robot arms have a force torque sensor on the wrist. So once you start grasping and moving it, provided it's not slipping, now the robot arm knows what the weight is.
How much power to
But the interesting bit is if you're trying to grab something and it starts to slip, because that means you're not grabbing it hard enough. And then the question is, have you got the wrong grasp, or is your grasp not strong enough, or is it badly placed, or is the object just too heavy for you? So that's why you want interesting sensing on the fingertips to be able to tell that slip is about to happen, so you don't break something or drop something.
How many kind of instances of that do you get? Like, does it happen quite a lot where it just breaks it, like the pint glass, for example? How many did you smash?
We didn't actually smash that many things. We did filmed a demo some years ago internally where we were handling some eggs from an egg box, picking them up and putting them down. And somebody walked in and said, yeah, but you guys are cheating, right? These are hard boiled. And that was the only egg that got broken, and it wasn't hard boiled. That's the robot wasn't breaking the eggs because we didn't set it to be crushing strength in any way. So one of the kind of key tricks in the design of this is to say, are you making a thing that's very stiff, or are you making something that's flexible? If you're trying to grab manufacturing parts on a production line all day and you know exactly what the parts are and the tolerances, you probably have a very stiff robot. It doesn't bend, it doesn't wobble, it doesn't, because it can grab something and hold it rigidly and move it exactly to where it goes. And if you watch a car production line flinging around entire body in whites through the mechanism, you're just like, yeah, that's a very stiff robot moving very, very precisely. We tend to build things that are flexible. There are sprung elements in there. There's some elasticity. So even if you're kind of grabbing something a little bit hard, there's give in the system. There's flex in it. That helps make it less likely to get broken.
And
basically.
is the robot able to determine that for itself, or do you have to tell it, this is fragile, go gently?
Both are possible. We measure to some extent the force we're applying. Because we've got tendons running down to motors, we can take a reading from those tendons, and that gives us a kind of how hard is it working. And you can say, don't work too hard, and then it won't. And that means it's kind of much, much softer. You can even say, essentially don't work at all, and then it becomes fully compliant. And that looks really weird because the robot sits there and you push it, and you hear the motor move as it drives the finger away from you because it's trying to make sure that there's no force on the tendons. So then it's suddenly very, very, it sits where you put it. But then you can say, okay, let's lock the joints down now, and then now they're really hard to move. There's a little bit of elasticity, but it's a controllable feature.
And are there any sort of current limitations that you see being overcome in the near future?
We're always looking for a better motor. That's something, and it's interesting because every so often someone comes along and says, I've got these new actuators and they're amazing, and we kind of get out the spec for the motors that we use, and we show them the spec for the motors that we use, and we say, so this is the kind of envelope we're looking for, and they go, That's pretty impressive, actually. That's which motors are those? And we go, they're the standard ones from Maxon in Switzerland.
Right.
And he goes, yeah. Because electric motors have got this like 150-year development pedigree. There's a lot, and some of the technologies in there, and when rare earths started being used in the magnets in motors, like the leap, really, really impressive. So competing with that is hard. We're always on the lookout for something that will.
Yeah.
I've talked a little bit about skin and the problems of sensors of touch, and that's always something that we're interested in. And the last thing that we're actually really excited by, and you're starting to see some results on this now, is people starting to use these new AI tools, the language models, and particularly the generative tools, the transformers, to start to write programs for robots that work automatically. Right. So I was talking to a colleague on the train on the way up about the DeepMind publication, where they're essentially getting a robot to do a task by writing a document that is the task that it's got to do, but instead of being written in English or Japanese or C++ or Python, it's written as a series of move to this coordinate, orient the tool at this, and it's just generating the exact movements that the robot makes.
Okay.
And we look at that and go like, that's new, and that's interesting because it's writing a program in the robot's effectively its own way of thinking, which is where am I in the world and how am I moving, and we can kind of see how we can grow on that and build on that. Okay. So I think there's going to be some fantastic stuff coming out from the kind of deep learning and transformer technology community in the next few years that will really cause robots to suddenly actually do lots more useful things.
Okay. And that you say that's how the robot kind of understands where it is, and that seems quite intuitive and like how we maybe understand the world.
Robots are very much kind of Cartesian coordinate creatures, right? A robot knows where the angle or the position of every joint. That's pretty much the definition of what a robot is. And it knows where it's putting that because that's all it thinks about. If you look at an industrial robot arm, you talk about the tooltip position and orientation, and that's kind of what you think about. With a robot hand, you look at the grasp and the pose, and that's about the positions of all the joints and then the location and orientation of that in space. So we're very Cartesian. We're very much thinking about that kind of 6-dimensional view of the world, point orientation and thinking of that. And so I kind of see that as almost the most fundamental level that a robot engages with the world in is what pose am I in, what position am I in. There's then a whole separate thing about perceiving, because of course robot is about action and perception. And for perceiving, you've got cameras, you've got sensors, you've got interpreting that, you're using that. And that's the bit where what we've seen with the deep learning community over the last 5-10 years, they've gone an amazing length with making robots that perceive, or making machines perceive better, being able to see things better in the world, being able to understand them, being able to read them, to recognize them, and so on. So as that technology advances, then you start to generate this stream of like, okay, how do we tell the robot what to do? And that's in terms of pose and orientation and contact and touch.
Okay. So with rapid prototyping technologies have come a long way. So as one of the longest running robotics companies in the UK, how has these advancements impacted the development and iteration process of the robotic hand today versus back then?
I mean, one of the really nice things that's happened in terms of manufacturing technologies is stuff that used to be really, really difficult got a lot easier. And part of that was just the invisible infrastructure got better. I can send you a CAD file and you can make it, and you're used to doing that, and we don't actually have to do 3 rounds of you making a part and sending it back to me and me going your tolerances are wrong on that bit and so on. We can all see the thing, and you can automate the process of inspecting it. I remember the first time someone had a system that would do small batch injection molding. They were 3D printing. Essentially, they were milling molds in not very good steel. And you could get 1,000 parts done on that mold. You couldn't get 10,000 done. You couldn't get 100,000 done. It wasn't like the molds Lego use that you can. It was just, but it was good enough. And it was done because they had the process set up right, so you could send them the CAD of the part, and they could automatically generate the mold, check their design rules on it, mill the mold, and then print and then injection mold the parts for you. Fantastic, complete game changer. We started using that for a whole bunch of pieces. In fact, we used it to make the fingers, but only the outsides of the fingers, because the reason for that, particularly odd, the outside of the fingers are very smooth. So it's actually worth having them made in a molding process where you can specify exactly the feel, the finish, the curvature. The inside has a whole bunch of fixtures and fittings and like mounting pegs and screw holes and so on. So we'd literally take these sprues from the injection molding, clamp them down on a plate and put them in the milling machine.
Right.
And
okay.
mill the inside
mill
of
the
them
inside
to get
out.
the right shape and the right
yeah.
nature of them in there.
Yeah. Okay.
So, would you say 3D printing has helped improve the advancements of the robotics company, as you can sort of print bespoke items sort of different to what traditional manufacturing methods can't really achieve, like injection molding or sort of CNC machining?
I think it makes it possible to print things quickly and to print a variety of things easily. So something we've seen people do is to take an object and make it in 4 or 5 different versions where you might change an angle. So we have some pieces that we use to calibrate, and they consist of a mount that you put a finger in, and the finger's at a certain angle.
Okay.
And there are 5 of those for 5 different key angles. So rather than produce 5 CNC processors to do that, we 3D print 5 different objects, and it's kind of easy to do that. And you can even do that semi-automatically, because you can basically use a generative CAD tool to say, here we are, here are the 5 different things I want, off we go. Can we machine those? Can we print those? Yep, great, that's good enough. If we need them at a really, really high level of tolerance and surface finish and so on, sure, then we can go and get them made differently. But for that loop where you're going, I want some things that are good enough, and I want them quickly, and I want them accurately, and I don't want to sit there going to and fro with a guy in Essex who runs a machine shop down there who's going to be like, it's only one of these. It's going to take quite a long time to set up. It's going to be, so you yeah.
Okay. All right. I thank you very much. Very interesting. If we want to find out a little bit more about you guys and what you do, where's the best place to do that?
Website, shadowrobot.com. There's loads of videos, blogs, discussions on there. If there's something that we said today that was interesting that we haven't talked about enough, let me know and I'll write a little piece for you on there, because there's a whole bunch of stuff on there that we write about that's kind of things that interest us, and we want to know what interests other people to write about as well.
Okay, thank you very much.
Thank you, guys.
And yeah, don't forget to like, follow, subscribe, share, do all the normal things that you need to do. And we'll see you next time on Prototype and See. Thank you.
Thank you.
Whether you're working on your first product or your 10th, you've got the Prototype and See podcast to back you up through your product development journey. Follow, subscribe, and tune in for our next episode. We can't wait to see where your prototype takes you.